All right. So you can all see it?
Yes.
Okay. So here's a couple of typical coax cables. RG8 is you know, the kind of the thicker kind, right? If you look on the chart here, it's almost a quarter inch, or you know, it's almost 4/10 of an inch thick. All these are kind of RG8 class coax. And in case you didn't know what the RG means, that's military terminology for radio grade. So you know that you got RG8, you got RG58. That's the smaller stuff. That's about actually less than half the diameter of the RG8. And in between is this RG8X, and I don't have a picture of it. I'll have to get a picture of it. But you see, it's a little bit larger than RG58, but somewhat less than the RG8, and because of that, it's much more flexible, you know, and less weight. So RG8X is a pretty good choice when RG58 is too lossy, which, you know, like at 10 meters it starts to get really kind of too lossy, and you don't want to use RG8X for whatever reason, like if you're hanging a dipole, you know, unless you're, you know, running like, you know, 1500 watts, you probably don't want to run RG8X because it's just so heavy, big and heavy, and very inflexible. So anyway, that's sort of the in my mind the good compromise level. You know, if you're going to mostly run 100 watts, you know, all these radios are 100 watts these days. No need to run RG8. But except
so it's RG8 is the thicker, heavier. RG8X is the kind of in between sides, right?
Right. And these two here are actually sort of the RG8X class. LMR is an actual manufacturer. So you see LMR 400, LMR 240. That's a particular manufacturer. But yeah, so it's a, you know, it's a good compromise. If you're not running a lot of power and you want it to be lighter and more flexible, like RG8X is a good compromise. So I'm going to skip over the first question in the study guide, if you're following along in the study guide, because as I was going through this, it seemed to me that would be better covered later. But so we'll start talking about coaxial cables. So there's a question: what are the typical characteristic impedances of coaxial cables used for antenna feed lines at amateur stations? Answer: 50 and 75 ohms. And, you know, mostly it's 50 ohms. The 50 ohms is sort of the standard we use in amateur radio. Sometimes you use 75 ohms because dipole antennas have a characteristic of impedance of about 75 ohms. So for example, I've used a 75 ohm cable before. And this is a little bit of a funny story. So I put this, I happen to get this 75 ohm cable kind of cheap. You know, ham radio operators are like cheap, right? That's sort of like, you say ham radio operator, you think cheap, you know? So I went to this local place, which was open at the time, called Purchase Radio. And I asked them how much for this call. You know, I said, you know, do you got any 75 ohm coax? Because I'm thinking I'm put up a dipole. And he had some, and he sold it to me pretty inexpensively. And I think Purchase Radio is one of these like old time radio stores, and he must have had this coax for a long time because it, like I said, it was inexpensive. So he must not have paid that much for it to begin with. I don't know how old it is, but so anyway, I put up this antenna, and I put my antenna analyzer on it, and no matter how I tuned the thing, I couldn't get it below 1.5 to 1. And I'm thinking to myself, what is this, Well, then it dawned on me, of course, that's 75 ohms. I have an antenna analyzer that's expecting 50 ohms, and you can do the math. That's a SWR of 1.5 to 1. And we'll talk a little bit more about SWR and impedance mismatches. But fortunately, the antenna analyzer I had at the time, you could set the sort of the default impedance, right? Because it's doing everything in the little computer in the instrument. And so I set it to 75 ohms base impedance, and then voila, I had a 1.0 to 1 in SWR. but here's the thing. So even though you can use it, right? There's no, and it presents a good match at the antenna, it's still not going to present a good match at your radio. Well, it'll present a match of 1.5 to 1, which isn't bad, but you'll want to somehow still match that 1.5 to 1 at your radio, because the radio will have a 50 ohm output impedance. So, like the IC7300, I use the IC7300 over and over here because it's a great example. It has a built-in antenna tuner, and it can tune SWRs, match SWRs up to 3 to 1. So that's nothing for the 7300 to do. So that's, but you still want to match the SWR at the radio, make the feed line match the output impedance. So anyway, 50 and 75 ohms is the answer here. And the vast majority is 75 ohms or 50 ohms. Another thing, so we just talked about old coax. Well, so I used this coax, this dipole for a couple of years, and maybe even more than a couple of years. But all of a sudden it started acting funny. Put my antenna analyzer on it. I got weird readings. I took it down and I said, well, maybe it's the coax. And I connected a dummy load at the far end of the coax, and then use my antenna analyzer to try and test the coax. And again, I was getting all kinds of weird readings. I mean, to this day, I don't really know what was wrong, but something was wrong with that coax. And that the rest of the coax I had, because I bought more than I needed, it just wasn't any good. Something went bad in it somehow. And so I ended up throwing it all out because it was, I don't know, I guess it got too old. So things can, coax can get old and then not be any good anymore. So the next question, so this is all then has to do with SWR, these next couple of questions. And so, this is a typical ham radio station, right? You got a transceiver, you might have an antenna, an external antenna tuner or an internal antenna tuner, and then you got a piece of coax that connects to your antenna. And just like we said in the tech class, oops. You want everything to be 50 ohms. When the if you have 50 ohm coax and a 50 ohm input impedance or 50 ohm input impedance antenna and a transceiver with a output impedance of 50 ohms, everything's matched. And what that means is that the SWR standing wave ratio in the system is 1 to 1. Okay. What happens when the SWR is a 1 to 1? Say, if you have a different input impedance out here, right? Say that's 100 ohms, not 50. You've connected a 50 ohm coax to it. Well, you have a mismatch there. And what happens when you have a mismatch? What'll happen is not all of the power you send to the antenna will get radiated. Some, so you have forward power here, and you'll have some power actually be reflected. Okay. So the question is, what might cause reflected power at the point where a feed line connects to an antenna? Answer, a difference between feed line impedance and antenna feed point impedance. And I'm going to suggest that you watch this video here. This video was made, it actually was filmed, now they turned into a video, by a guy at Bell Labs in the 1950s. And fortunately for us, antenna physics hasn't changed since the 1950s. And he uses a mechanical machine, actually. And why can he do that? Because wave behavior is the same, whether it's a mechanical wave or an electrical wave. And he uses this machine to show wave motion and wave behavior. And he can, if we had time, I would show it here, but it's a half an hour long. So I really don't have the time to do it. But, this machine allows you to see a wave propagate along a medium. And by putting a mechanical device on the end of it that simulates the antenna, he can match the mechanical impedance to the transmission line impedance, and shows that when you've got that match condition, there's no reflected power. When he changes that mechanical impedance at the end, it shows a reflection. And what happens is you get a wave going forward, a wave going backward, and it's that superposition of waves going forward and waves going backwards, that generates the standing wave on the transmission line. And the bigger the mismatch, the more the higher the voltage, basically, the higher the reflected voltage, the reflected power, which then translates into a higher voltage. And so the standing wave ratio is the ratio of the maximum voltage on the line to the minimum voltage. And when more power is reflected, you get a higher maximum voltage. So you get a higher SWR. And
Dan, can you copy the link on the chat?
What do you mean by copy it?
Just like copy paste.
Oh, yeah.
URL.
Good. Well, I have to type it in, but I could do that.
Never mind. I thought it was something you can.
Yeah, no, this is all like pictures here. So
gotcha. Don't worry about it.
I'll put this in the email I send. So if you don't want to write it down now, I'll put it in the email. And this video really shows it. It shows it very graphically, and it's a very good explanation. So when there is a match, though, the SWR is 1-to-1. That's when you transfer the most power from your radio here, the radio system, to the antenna, and then the antenna will radiate the most amount of power. Question, what standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having 50 ohm impedance? Answer, 1-to-1. That's the holy grail there, 1-to-1. Question, what must be done to prevent standing waves on an antenna feed line? Answer, the antenna feed point impedance must be matched to the characteristic impedance of the feed line. And this question is really not, it's not quite right, but I think you get the idea. If they should say reflected power, what must be done to prevent reflected power on an antenna feed line? But again, it'll be matched when the antenna feed point impedance matches the feed line impedance, then you have a 1-to-1 match. And one reason that's important is because if you're using coaxial cable, if you're using coax, the losses in the cable go up as the SWR goes up. So you have a couple ways to lose power in a coaxial feed line. One is with frequency, right? The higher the frequency, the more loss you'll have in the cable. But the higher the SWR, the more loss you'll have in the cable as well. Where am I here? Now, the SWR, the standing wave ratio, is also equal to the ratio of the feed point impedance to the feed line impedance. So that's the thrust of these next couple of questions. What standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having a 200 ohm input impedance? Well, it's 200 over 50, or 4:1. What standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having a 10 ohm impedance? Well, it's always greater than 1. So in this case, you got 50 over 10. So the standing wave ratio will be 5:1.
Dan, I'm confused on this. The first question, it's 50 over 200, so that looks like 1:4, not 4:1.
That's 200 over 50.
No, both these questions read exactly the same. In the second question, you put 50 over 10.
Yeah, I know. Because
and in the first question, it's 50 over 200.
Right, because the SWR is always greater than 1, right? And actually, these are just ratios, but we always express it as something to 1.
Okay.
And so it's not the really the absolute value here, but the ratio, if that makes any sense. Like if you had a 250 ohm input impedance here, you'd still have a 5:1 standing wave ratio.
So you're telling me that the first question, if it was 200 ohm feed line over 50 ohm impedance, it would still be expressed as 4:1.
Exactly.
Okay.
Yeah, exactly. And once you take a look at this video, you'll see why, because it's the ratio of the impedances that cause the reflection. Not so much the actual values, but the ratio of the values. So this next one is kind of an interesting question. If the SWR on an antenna feed line is 5:1 in a matching network, such as this antenna tuner, and a matching network at the transmitter end of the feed line is adjusted to 1:1 SWR, what is the resulting SWR on the feed line? So if you have a 5:1 SWR here, you can adjust this antenna tuner so at this point, the SWR is actually 1:1. Makes the transceiver happy. Oops. That makes the transceiver happy. But you still have this 5:1 SWR on the transmission line. And like I said, the higher the SWR, the more losses. So you still have that loss here in the feed line, but at least the transmitter will be happy. So you're still not getting, you're sort of fooling the transceiver into thinking that it's in a matched system, which is good for the transceiver, but still not good for your signal. So if you have a 5:1 SWR and you're using coaxial cable feed line, you still want to fix that, is what it amounts to.
And question.
Yeah.
So why would you use an antenna tuner if it really is doing nothing except faking out the transceiver to think it's got a match?
Well, because you're still, well, because okay, that's a good question. So what's bad about reflected power? Well, the power has to be dissipated somewhere. right? So if you didn't have this antenna tuner here and you just connecting right through it, that reflected power is going to come down and it's going to come back into your transceiver, and it's going to get dissipated in the transceiver. And that may or may not be good. You know, your transistors will heat up, and that's probably not a good thing.
Okay, so it's really not so much making the antenna transceiver relationship work better. It's really more of preventing damage to the transceiver.
Right. And what'll happen, actually, to take the IC7300 again, what'll happen is that transceiver will detect that there's a 5-to-1 mismatch, meaning it's going to be getting a fair amount of reflected power, and it'll actually crank back the output power. You may have it set for 100, but it's at 5-to-1 output, it's going to crank it back down to, like 20 watts maybe or less, because the reflected power is a ratio of the power of the forward power, and that means less power is going to have to be dissipated in the transceiver.
So the lesson is, don't wait for your antenna tuner to fix your antenna problem. You got to fix it on your own.
Right. And I was talking about this flaky antenna I had. I was doing that, and which was not good, but I didn't have to go outside and screw around with the antenna. So at the time I had an IC746 Pro, which had a similar antenna tuner in it. It had those antenna tuners are really only good up to about 3-to-1 SWR, and I knew I was at the hairy edge of that, but I don't know. I was lazy to go out there and fix the antenna. And finally it got bad enough where the internal antenna tuner wouldn't even tune the antenna. So then I had to do something, and then I ended up replacing the antenna. That's when I figured out the coax was bad, and I needed to do something totally different. So the question is, why would you want to do that? Well, if you're not too fussy and you just want to make some contacts, and even if you got a high SWR antenna, who cares, But if you want really to get the most performance, you want to, make sure that you have a good antenna system, and that your antenna feed point impedance matches the coax. Up to, they say up to 2-to-1. If you have a 2-to-1 mismatch, that's really not so bad. There's some charts that show, and I probably should add a chart here, shows that at 2-to-1, the forward power is such and the reflected power is whatever ratio that is. Up to 2-to-1, it's really not so bad. Once you start getting above that, then you might want to be a little concerned about that. And usually at 2-to-1, that's when the transceivers start cranking back the output power. But on the other hand, if you were on a boat with your radio and your boat was sinking, well, you just get on, and no matter what the SWR is, and call it SOS. I mean, it's that kind of thing, right? If in a real emergency, do whatever it takes. But when it's not an emergency, to keep the antennas in good tune. Any questions so far? Any other questions? So here's the next question. I talked about this a little bit already. What is the interaction between high standing wave ratio, SWR, and transmission line loss? Answer, if a transmission line is lossy, high SWR will increase the loss. So that's actually not even just when it's lossy, but if it's just in general, a higher SWR will increase transmission line loss. This is kind of an interesting question. What is the effect of transmission line loss on SWR measured at the input to the line? Answer, the higher the transmission line loss, the more the SWR will read artificially low. And why is that? It's because if you're losing power in the feed line, well, the voltage at this point, the voltage ratio of the standing wave ratio will be lower because you've lost some power here. So the voltage here will be lower. You know, it's almost like you had, you know, resistors in the feed line, right? They're dropping the voltage. In fact, you know, we joke about this on field day. You know, what do we do on field day? We put up these antennas, we go out in the field and we put up these antennas, and you know, you have to space them fairly wide apart because if you got multiple stations, you don't want them interfering with one another. So you run, you know, sometimes crazy long coax runs out to these antennas, which results in a fair amount of loss if you got 300 or 400 feet of coax. And one time I was talking about this with a guy, and he says to me, he says, "Yeah, what does it matter? It's field day." He says, "But you know, by the time that reflected power gets back to the transmitter, you know, there's going to be no SWR there anyway because the voltage will have dropped so much." Well, what does that mean? That means that really you're not radiating that much power either, but it's field day, you know, you just sort of go with the flow. And field day, you know, you almost don't care too much about absolute performance, although you kind of should, but you don't really, because the whole idea is just to make contacts, and there's so many stations on, you can make contacts even if your antenna system is not perfectly tuned. So anyway, this is like a field day phenomena that with really long coax runs, you get the transmission line losses will make the SWR read artificially low. I also talked about attenuation losses as the frequency goes up, right? So at 80 meters, you know, RG58 is just fine. But at 2 meters, you don't want to be using RG58, especially for long lengths of coax, because it'll just eat up the signal. At that point, you're wanting RG8X or maybe even RG8. You know, if you're got a 2 meter antenna on top of a tower, a 50 or 60 foot tower, you know, you actually might want to you know, run RG8 in that case, just because the losses will be lower. So question, how does the attenuation of coaxial cable change as the frequency of the signal it is carrying increases? Answer, attenuation increases. In what units is RF feed line loss usually expressed? Answer, decibels per 100 feet. So that's where the decibels comes in again, is like if, let's see if this even says it here. Yeah, so here's like some attenuation figures right here. And that's at 150 megahertz, right? The value is in dB per 100 feet at 150 megahertz. So this RG8 is 2.2, LMR 400, 1.5 dB. RG58 is 6.1, though this is a 6.1 dB. Well, if you remember, a dB, 6 dBs is a ratio of 4:1. So if you're using 100 feet of RG58 and you're pumping 100 watts into it at 2 meters, you're only going to be radiating 25 watts out of your antenna. Whereas here for 1.5 dB, that's going to be more like well, less than 2:1, probably more like maybe 1.5 or so. So you know, you're going to be radiating, you know, 60 or 70 watts instead of 25 watts. So that's where you really want to, you know, don't want to use RG58 on 2 meters, and you want to, as you go up in frequency, this only gets worse. This difference only gets worse. Any questions about that? Okay, so I'm going to jump back to the question on parallel feed lines. And where's my Parallel conductor feed lines. So mostly we use coax in amateur radio stations, but there is some advantages to using what's called parallel conductor feed line. And there's really three basic types. 300 ohm twin lead. If you're old as I am, you remember that as being the TV, the cable that connected your TV antenna to your TV. Why did people use that in like the 50s and 60s? Because it has very low loss. Then you have 450 ohm ladder line and 600 ohm open wire feed line. These are all variations on a theme. Question: which of the following factors determine the characteristic impedance of a parallel conductor antenna feed line? Answer: the distance between the centers of the conductors and the radius of the conductors. So this isn't probably quite to scale, but it's close. And you'll see 300 ohm twin lead is pretty closely spaced. 450 ohm ladder line is a little bit wider spaced, and 600 ohm open wire feed line is probably about 1.5 inches or 2 inches between the conductors. And one of the cool things is you can actually build your own open wire feed line. You see here they're under the 600 ohm. Let me create a layer here. These things here are spacers that you can buy, and you go to Home Depot or something and buy some 14 gauge wire and make your own feed line. I'm currently using, in my station, 450 ohm ladder line to connect my antenna to I have a tuner, an antenna tuner, and that works great too. It's a little bit beefier than the 300 ohm twin line, can carry more power, and but even so, I think next time I put together an antenna like this, I'm going to try this 600 ohm open wire feed line just for kicks, just to do it. What's a reason to use for this kind of open wire feed line or parallel conductor feed line instead of coax? Well, this doesn't have the same SWR loss that coaxial cable does. So if you like my antenna right now, it's just it's called a doublet antenna, kind of like a dipole, but it's not resonant. The length is whatever I can put up. And then it's connected with this ladder line. And in my shack, I have an antenna tuner, and I run that into the radio. Well, why does this work? Well, even though I don't even know what the SWR is on the antenna. It's because it's unresonant. It's non-resonant. I'm relying on this antenna tuner to be able to create a 50 ohm impedance at this point. And this is a chunk of coax connecting the antenna tuner to the radio. And this works great. And the reason it does is because I don't get, it's a lot lower loss in this 450 ohm ladder line than it would be with coax. One time a guy, we were at a test session, and he had sat in on part of the class, and it was a one-day tech class. And I mentioned to the students that I was using this 450 ohm ladder line. And the guy says to me afterwards, he says, I never had the guts to use 450 ohm ladder line. Well, in a way I didn't either, but man, once you do, you love it because there's nothing to go wrong with it. With coax, so you get water in there and it degrades the shield, and it can affect the dielectric. Here, who cares about water? Especially with open wire feed line, because water will get on the wires maybe, but who cares? It's not going to degrade the wire. So it's kind of a cool thing. And then there's another question here. What is typical characteristic impedance of window line parallel transmission line? Answer, 450 ohms. So it's ladder line or window line. These are the windows. What was I going to say? Oh, you know, this is a funny thing too. You can sort of see it here even. If you look at this window line, ladder line, you think, well, the size of these windows and the length between them would be equal and regular, but it's not. You can almost see here, this is smaller than this one. I don't know why they do that, but that's what they do with ladder line.
Isn't that just to let the wind blow through it?
I don't know. I really don't know. Actually, in what you do, what you're supposed to do, which I've done here, is actually twist it, because that'll deflect the wind, right? Instead of presenting really a high wind load, it presents less of a wind load if you twist it. All right, any questions about that?
Yes. Is there any gizmo I've seen that's attached to the 300 ohm line that makes it a 50 at a connection? I thought I saw one in one of my junk boxes.
Oh, well, good. Yeah, that's a good question. So what you want is what's called a balun. Okay, and this does two things. First off, these kind of feed lines are called balanced feed lines. Yeah, they're symmetrical, right? They're balanced. You connect the parallel feed line out here. This is the balanced side, BAL side. This is the unbalanced side. This is where you connect a coax cable. Coax is not really symmetrical, right? The two conductors are not symmetrical at all. So it's unbalanced. So this provides a balanced to unbalanced connection. You can get these in a number of different ratios. 1-to-1, 4-to-1, 9-to-1. I think I've seen some 6-to-1, but these are the more common ones. Why is that? Well, this is, the impedance transformation, and that's what you're doing here. You're changing the impedance, right? The impedance transformation is based on the square of the difference of the two, or square of the ratio of the two, the primary turns to the secondary turns. So if the primary is equal to the secondary, you get a 1-to-1. So that's no transformation at all. If the secondary is has a half of the turns as the primary, and vice versa, you get a 4-to-1. By reverse, I mean, it could be, if it's 4-to-1 this way, it's 1-to-4 this way. This would be 4 times whatever this is. And then 9-to-1 is when you have a ratio of 3. The turns ratio is 3. But balun is what you're looking for.
Does it matter what, there's two separate lines basically on that lateral line, and then it goes into a coax. Does one line have to match the center and one line have to match the ground?
No, because it's balanced. That's the beauty of it. It's balanced, so it doesn't matter. And so, well, we'll talk about this a little bit more in dipoles, but so if you're going to feed a dipole with coax, right? What do some people suggest you do? They suggest you put a balun here. Why is that? Because you're going from a balanced system, symmetrical system, to an unbalanced feed line. what the balun is supposed to do, because, so we say it's balanced, but, you're never going to get this length exactly this length. So it's going to be there's going to be some amount of unbalance there. What the balun is supposed to do is force the same amount of current into this leg as goes into this leg. And why is that? Why do you want that? Because when you got coax there, let me see if I can draw this somehow. So here's the center conductor of the coax, and here's the shield. I'm going to draw this sort of like this. Well, when everything's perfectly balanced, and remember, RF energy flows near the surface of a conductor, right? So when this is perfectly balanced, the current on the inside of the shield is going to equal the current on the center conductor. But if there's an imbalance, you'll actually get some current on the outside of the shield as well, because it's imbalanced. So that current's got to go somewhere, and it goes on the outer shield of the coax. That's not good, because then the outer shield becomes part of the antenna system, and in worst case, it can detune the antenna and even cause unwanted radiation from the coax, which can cause RFI problems. So that's why they always say use a balun here, because then you're forcing it to be balanced, and you won't get into this problem here. Now, so I've run many dipoles without balance. So the question is, how much imbalance is bad? Like say if you've got a 60 meter or 40 meter dipole here, right? It's typically 33 feet on each side, right? Well, what if this was 32.9 feet? Is that amount of imbalance bad? I don't know. I mean, I've never done any like experiments to see, but my gut feeling is that little bit of imbalance is not going to create a big problem. Although it might. If one was 33 and 32, I don't know. Maybe at that point you're getting to enough unbalance so that you do need the balun in there. But that's the theory of balance, and that's how you get that. You're getting back to your question. That's I think that's what you're talking about, is something to transform the 300 ohm or 450 ohm here into something that you can connect a coax to.
So basically, if you have a long run, you could use that 450 ohm ladder line, say from the antenna to the house, and then going through the walls, you could have a coax connected to it and go down to the transceiver.
Yeah, theoretically. Although you really don't want to, you really want to have something more like this, and the reason for that is you actually get a impedance transformation. So even though this might be, if this is a perfect dipole and say 72 ohms, right? This is going to actually, you still don't really necessarily know what the impedance is here, because it's dependent on the length of that line. And in fact, there's some antenna systems that use lengths of 450 ohm ladder line to give you a 50 ohm impedance at this point. And then if you do have that, if you have just the perfect length here, then what do you want to do? You want to use a 1-to-1 balun and convert that balanced load to an unbalanced feed line.
So Dan, if coax is has so many problems as it looks like, why doesn't everybody just use parallel line all the way?
Well, you know why? Because I mean, it's just like anything in any engineering discipline or situation, there's trade-offs. The trade-off with this is that you can't like run this close to metal objects, right? If the antenna was on your house, you don't want to run it over your metal gutter because that metal gutter is going to detune that line where it runs over the gutter. If you remember the old twin leads, they had standoff insulators that you had to put on your house to stand it off from the house, right? If you I don't know if you remember that, but and why was that? Because if it came too close to any metal, it would not be 300 ohm twin lead anymore, and it would be some other unpredictable impedance there.
So the shield is providing some
Exactly.
kind of protection on coax,
Exactly.
even though you're running half
you can
the
run
signal.
coax. Like you don't. Another thing you want to do is lay this on the ground. Although some people do and they get away with it, but you don't want to lay this on the ground. Why? Because then you get more ground losses. With coax, you can throw it on the ground. It doesn't matter. In fact, like on field day, we don't do well. Some coax. In fact, let's go back to that. Here, this you see here, right here. There's a type called berry flex. It's made to be buried, right? So if you're running coax out to, something in the back of your yard, you might want to bury that coax. You can't bury open wire feed line, parallel conductor feed line. So there's trade-offs. There's trade-offs on both. Good questions though. I love the questions. Should we move on here? We actually have a fair amount of stuff to cover here, and we probably should keep going here. I'm going to skip the questions about random wire. I don't know why I haven't had my glasses on all this time. I'm going to skip the questions about this and go right to the dipole antenna. We'll come back to this question. So this is the half wavelength dipole antenna, most common antenna in amateur radio. 2 pieces of wire, each a quarter wavelength long. One's connected to one either the center conductor or the shield of the coax. The other one's connected to the other one. You notice in this case, I'm not using a balun here, right? There's no balun in this one. And like I say, you can kind of get away with it if you're careful enough to keep these 2 sides as balanced as possible. The rule of thumb for the length of an antenna, dipole antenna, is 468 over the frequency in megahertz. There's an article in a 1920 QST where the guy came up with this formula, and he did it mostly by experiment. And whenever you put up a dipole antenna, you always have to trim it. You always have to adjust this length to tune the antenna. And why is that? Well, there's a lot of factors that can affect the antenna. So if it was totally in free space, then the quarter wavelength would be fine. But there's like stray capacitance and other stuff that affects the length. So you always end up having to tune it. If you cut these wires to this length, however, chances are you're going to, and when you do this, right, you want to have more than enough wire, right? So, and then at the ends, you'll wind it around so you can adjust it longer or shorter, right? Although if you use this, mostly you'll be long, which is good. In fact, I sometimes joke that the guy who came up with this said, yeah, really it should be like 462, but the amateurs, they'll cut it to 462 and then they'll have an antenna that's too short. So I'm going to say it's 468 and then they'll always have enough wire. So, but this is generally the rule of thumb for that.
So Dan, is the length across the
The top.
entire antenna?
Exactly. Yeah.
Just the quarter or the whole thing? The
I
whole
should put that in this.
Got it.
Yeah. So you use this, then you cut, measure the wire, cut it in half. And so, and that's a good thing to do too, is to cut it in half. Why? Because you want to try and maintain this balance as much as possible. You want this length to be, pretty close to this length, so it's as balanced as possible. So question, what is the approximate length for a half-wave dipole antenna cut for 3.550 megahertz? Well, 468 divided by 3.55 is equal to 132 feet. And it's not exactly, I forget. Let me get my calculator out here. I actually ran through this calculation earlier. I should have wrote it down. $468 divided by 3.55. It's 131.8. But 132 is the answer. That's as close as.
The closest answer, 132.
Yeah, the answer is 132. Question, what is the approximate length for a half-wave dipole antenna cut for 14.25 megahertz? 468 divided by 14.25. And it's the answer is 33 feet, but it's, if you put it in your calculator, it's 32.8 feet. So just remember 468 over, probably if you did the like 300 over the frequency in megahertz, you'd come up pretty close too if you use that equation. But this is the official amateur radio equation. So this is they say this impedance here is like 72 ohms, but really that's only if it's in free space, and if it's fed right at the center. If you and you can do this, but if you feed it like a little away from the center, the impedance will go up. So, question, how does the feed point impedance of a half-wave dipole change as the feed point is moved from the center toward the ends? Answer, it steadily increases. There's a type of antenna called the off-center fed dipole. And what you get is, 1/3 of the antenna here and 2/3 of the antenna here. And if you feed the antenna there, you get an impedance of about 200 ohms. The amusing thing about this is it's 200 ohms at the fundamental frequency, but also at harmonic frequencies. So if you cut this antenna for 80 meters, then it'll be about 200 ohms on 40 meters, 20 meters, and 10 meters. So even with one set of wires, you get a basically a 4-band antenna. And what do you do to get, because you're going to feed it with 50 ohm coax, right? You put a 4-to-1 bal in there, and it'll transform it to about 50 ohms. It's the off-center fed dipole. Oop. Sometimes they call this a Wyndham antenna, but it's not really a Wyndham. Wyndham was it's a similar antenna, but it's a little different. Question: which of the following is an advantage of a horizontally polarized dipole? I guess I must be missing a word here. As compared to a vertically polarized HF antenna. Answer, lower ground reflection losses. So, think about this. So this is, some amount of space between there. And if you got a vertical antenna, and we'll talk about quarter wave verticals in a minute, it's close to the ground. So some of the radiated power is going to go into the ground and be lost in the ground. You get some ground losses here. So you get lower ground reflection losses with the dipole, horizontally polarized dipole. Any questions so far?
Yes. Does it make much difference if it's copper, aluminum, or anything like that? Different metals?
Not that much. What I would be hesitant to put up an aluminum dipole only because, it's not strong enough wire. It's probably it's a mechanical thing more than an electrical thing. Because you're not, unless you're running really high power, you're not putting that much current through it. So, but I would that aluminum, I would probably shy away from aluminum.
The typical height of that horizontal antenna?
I say again?
What would be the typical height above the ground?
As high as you can get it. I mean, seriously. Generally, they say you want to be, you want to shoot for like at least a quarter wavelength, and a half wavelength would be best. Because you will still get some ground reflection, right? You'll still get some ground reflection, and that'll change the pattern. In fact, there's a question here. Which of the following best describes let's talk about the radiation pattern first. So let me do this. So if you took a top-down view here, let me do this. You took a top-down view of this dipole. The radiation pattern is such that you radiate the most energy broadside to the antenna. So you're going to radiate mostly here, little here. But if it's not high enough, then the radiation pattern changes because of ground reflections. So question, which of the following best describes the radiation pattern? Well, that's a quarter wave antenna. Let's see. Yeah, so the question, what is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? So that's this. It's a figure 8, right? So it's figure 8.
Okay, come here. Come on, let's get up on the bed.
How does the antenna height affect the horizontal azimuthal pattern of a horizontal HF dipole antenna? Answer, if the antenna is less than a half wavelength high, the azimuthal pattern is almost omnidirectional. So this pattern changes because of ground reflections to, more omnidirectional. Question, how does the feed point impedance of a half-wave dipole antenna change as the antenna is lowered below 1/4 wave above ground? Answer, it steadily decreases. And again, that's because of ground reflection. So, all this stuff we talk about dipole antennas, it's only when you can get it up in free space. And that's another reason why you tune it here, right? Because, if it's not real high, then the ground is going to have an effect on the feed point impedance. So does that answer your question?
Yes, it does.
Okay. All right, let's talk about vertical antenna. So here are 3 different configurations for the quarter wave vertical antenna. And I should have shown this, but if you have a dipole antenna, you know, you're sending current into the antenna, right? So it's going this way and it's going this way. And the field is being set up between these two elements, right? The RF field, the electromagnetic field. You have two elements, so that's good. When you have a vertical antenna, however, you don't have that, right? So you have to generate the field between the radiating element and something. In the simplest case, you might have a ground rod here, and the field is going to be between the radiating element and ground, in that ground rod. This is actually how when I was a novice, I had a 14 ABQ vertical. Someone mentioned the Hustler antenna before. You know, the 14 ABQ was the high gain version of that Hustler antenna. And this is what I did. I sunk an 8-foot, my dad was great. He helped me do all this stuff. He sunk an 8-foot pipe into the ground, and I operated the vertical antenna against that, basically against that pipe, you know, and the coax was connected here. That worked. It didn't work the best. What would have worked better is if I'd actually laid some radials out here, right? Then I would be generating the field between the radiating element and all these different verticals. So I'd have more, I don't know, for want of a better word, sort of options, right? That there'd be more space for that radio wave to be generated. Sometimes we bury these radials under the ground. And yeah, that works okay. And it keeps the wires out of the way so you don't like chew them up when you're mowing the lawn. But it's been shown that it's best if you can keep those radials above ground, because then you don't get as much ground loss. So this is, I don't know what you want to call it. I don't know. This is called the ground plane configuration. Here the degree, the angle between the radials and the antenna is 90 degrees. 90 degrees. Here, if you've got the radials at a 45 degree angle, call this a ground plane configuration. And let's talk about feed point impedances. So the dipole has a feed point impedance of 72 ohms. Well, here you got like a half a dipole, right? So what would you expect the impedance to be? Well, it's about 35 ohms. So it's 35 ohms in both these cases. Here, if you angle the radials, though, you get a feed point impedance of about 50 ohms, which is a better match to coax. You know, if you can still feed this with coax, but you're going to have about a 1.5 to 1 SW. Oops. 1.5 to 1 SWR. Here, if you got 50 ohms, then you've got pretty close to a 1 to 1 SWR.
Hey Dan, question: would there be a difference between a receiving antenna versus a transmitting antenna, or does a transmitting antenna make for a good receiving antenna?
Well, the question is depends. Depends what band you're operating on and all kinds of different things. Mostly the antenna we use for transmitting, we use for receiving as well, but not always. And in fact, we'll talk about toward the end of this chapter. There's discussion of some receiving antennas, and I'll talk a little bit about that later. But mostly, we use the same antenna for receiving and transmitting. So the dipole, right, has a figure 8 radiation pattern. The vertical, though, has an omnidirectional pattern. And this is one reason why you might want to use a different antennas, two different antennas, even on the same band, right? You know, there's a null here, but if you're using a vertical, that signal is going to come in a lot stronger than here, right? The other thing about a vertical antenna is it has what's called a low takeoff angle. So, you know, this, you know, it's not very good drawing, but here you have a low takeoff angle. If you had a high dipole, then, you know, you have a higher angle, and it's the distance bouncing off the ionosphere is shorter. So that's a nice thing about a vertical antenna is you have a low takeoff angle. So if you can't put up a beam, you might want to think about verticals because, you know, they have a low takeoff angle. I don't think there's questions about that, but that's the idea. So question, which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? Answer, omnidirectional in azimuth. And azimuth is sort of the plane on which the antenna is radiating. So it's the, you know, east, west, north, and south kind of thing, rather than up and down. That's the elevation pattern. Question, what is the approximate length for a quarter wave vertical antenna cut for 28.5 megahertz? Well, if L was 468 for a dipole, it's 234 for a quarter wave vertical. 234 divided by 28.5, and that's about 8 feet. Question, where should the radial wires of a ground-mounted vertical antenna system be placed? Answer, on the surface of the earth or buried a few inches below the ground. So that's, that would be this kind of configuration. Question, what? Is there a question? Okay. Question, which of the following is a common way to adjust the feed point impedance of a quarter wave ground plane vertical antenna to be approximately 50 ohms? Answer, slope the radials downward. That's this situation here. And if you think about it, if you sloped it 90 degrees, what do you got? Well, you got a dipole, right? And that's going to be 72 ohms. So, you know, 50, if you got it 45 degrees, 50 ohms is about not quite halfway between 36 and 35 ohms and 72 ohms. So as you bend those radials down farther, the impedance is going to go up. If you can only get 30 ohms, well, you're not going to get quite to 50 ohms.
Dan, what about an antenna that's magnetically mounted to like a car hood?
Yeah. So they're using a mag mount, right? And here's the car hood. There's some amount of coupling between the car roof and so the coax coming in, the center conductor is going to go here and the shield's going to go to here and it's going to be coupled to there. So the car roof is providing the ground plane for the vertical radiator.
So is that going to be like the 90-degree ground plane here in the middle?
Yeah, probably more like that. All right, any questions about this? All right, so let's just talk real quickly about random wires. There's one question about random wires. So you can throw up a random wire antenna and just as the name implies, it's just a piece of wire that runs wherever, you know, length unknown. when you got something like this, I mean, you really don't know what the impedance is going to be here. So you probably want to have a tuner in here, right? An antenna tuner. And hopefully the antenna, well, let's. Hopefully, whatever the impedance is here, this antenna tuner will have enough range to change it in the 50 ohms here. So part of the problem that happens here, right, is that you still need, you know, this is two conductors here, right? It's in the coax, and you only got one conductor here. Well, you you have to have some place for that field to be generated, right? So it's actually going to come back to your antenna tuner, and you know, if this is in your shack, that can create some RF voltages on the chassis of these units. That's why I said that's where the counterpoise comes in, right? If you have a counterpoise, then the field gets generated between the random wire and the counterpoise and not here so much. But question, what is one disadvantage of a directly fed random wire HF antenna? You may experience RF burns when touching metal objects in your station. And that's because of this phenomena here.
Dan, how is this different than an end-fed antenna?
Okay, good question. So an end-fed, again, you have to have an antenna tuner with an end-fed. An end-fed is usually, not always, a half wavelength long. And what does that tell you? What does that do for you? Well, you know, the impedance at the center is 72 ohms, right? And one of those questions says, what happens as the impedance as you go toward the end steadily increases? So the impedance at the end is going to be in the thousands of ohm range, say 5,000 ohms. So you have to have some kind of bell in there as well as an antenna tuner to transform that into 50 ohms. But you get the same radiation pattern from this end-fed half wave. End-fed half wave, that's an EFHW, that's what that stands for, as you would a dipole antenna. I'm not a big end-fed guy. I you know, all these people say, oh, end-feds are the greatest and blah, blah, blah. And I just don't see it. I mean, they'll tell you, oh yeah, I put this antenna up and it works great, tunes up on every band, and I work all kinds of DX with it. But you know, I just don't think it's as good as just a plain dipole, or like in my case, a non-resonant doublet antenna.
Thanks.
Yep. All right. Let's talk about directional antennas. We call it, you know, it could be a beam antenna, Yagi antenna. These are all terms for directional antennas. Beam, Yagi is a particular type of beam. Quad is another one. We'll talk about the quads. Dish antenna is also a directional antenna. This is the pattern for a 3-element 20-meter Yagi antenna. And you can see from this that it's going to radiate. Oh, what happened there? It's going to radiate. Oh, heck. It's going to radiate. Oh, heck, what happened? It's going to radiate more power in this direction than in this direction. So question, which there's a thing called reciprocity, a principle called reciprocity. That means it's going to receive better in this direction than it will in this direction, right? And certainly better than from this direction. So that's the thrust of this question. Which HF antenna would be the best to use for minimizing interference? Answer: a directional antenna. So if there's a station out here that's causing you interference, if you swing that beam such that the main lobe is in this direction, you're going to be receiving very little of the signal coming from this direction. So that's the thrust behind this that question right there. Now, let's think about this. The dipole antenna has a figure 8 radiation pattern, right? That's probably a little bit more. That's a little bit better. So the gain of a dipole, the gain of this beam antenna over the dipole would be this bit here, right? And if these are in dB, let's see how much, see if it's probably not quite this good, but if each of these is 10 dB, right? Then I've got a 15 dB gain antenna here. It's probably not quite that good. You're probably not going to get an antenna 3-element beam to be 15 dB. And because this is a dipole, we say this is 15 dBd because it's referred to a dipole. Then you have an isotropic antenna. The isotropic antenna, there's really no such thing as an isotropic antenna. It's just a point source from which all that radiation radiates, all 360 degrees, and actually in 3 dimensions from that single point. Well, that's just a theoretical antenna. You never have an actual antenna, and a radiation from an isotropic antenna might be something, well, it might be like right along this 20 dB line, actually a little bit farther out. Because the difference between dBi and the gain over an isotropic antenna is referred to as dBi, isotropic. I stands for isotropic. And so then the figure, the gain would be a little bit more than for the dipole antenna. And sorry about this sloppy drawing here, but dBi is greater than dBd by about 2.15 dB. And like I say, I didn't really draw very well, but this would be about 2.15 dB. It's good to know this because, dBd will give you a better expectation of how the antenna will perform rather than dBi. But if you know this value, then you can make the conversion. Why do antenna companies specify a dBi? Well, it makes their antennas look a little bit better, and probably just a figure that comes out of their computer programs. So question, what is meant by the terms dBi and dBd when referring to antenna gain? Answer, dBi refers to an isotropic antenna. dBd refers to a dipole antenna. And actually, I should have said this, but whenever you're talking about gain, you're talking about gain with reference to another antenna, right? Because that antenna itself doesn't have any gain, right? You can't get more power out of an antenna than you put into it. You can get more power in a particular direction, and that's only when you compare it to another antenna. Question, how does the antenna gain stated in dBi compare to gain stated in dBd for the same antenna? Answer, dBi gain figures are 2.15 dB higher than dBd gain figures. Any questions about that? All right. Let's look at another thing. So this, again, this is the radiation pattern. There's a thing called the front to back ratio. And that's the gain in the forward direction. And this is called the main lobe. That's the forward direction to the rear. So front to rear. And when they draw these radiation patterns, the radiation in the forward direction always hits these axes at the 0 dB point. So this outer ring is 0 dB. So then you can just read this off. So in the reverse direction, it's about 28, right? So in this case, the front to back ratio is about 28 dB. Question, what does front to back ratio mean in reference to a Yagi antenna? The power radiated in the major radiation lobe, well, sometimes they call it main lobe, major lobe, compared to the power radiated in exactly the opposite direction. Question, what is meant, and this is where I got main lobe from, what is meant by the main lobe of a directive antenna? Answer, the direction of maximum radiated field strength from the antenna. So that's that direction. This is the main lobe. I actually dinged them on this. I said, you know, you should make these two questions match each other. You shouldn't use two different terms for the same thing. And they basically are the same thing. All right, any questions about that? So this is a very simple diagram of a 3-element Yagi antenna. It'll have 3 elements, a reflector, the driven element, the reflector, and the director. As you can see here, the reflector is a little bit longer than the driven element, which is a little bit longer than the director. The difference between these is about 5%. So the reflector is 5% longer than the driven element, which is 5% longer than the director. And when set up this way, the major radiation lobe is this way. So this is directive in this direction, from reflector to director. Question, what is the approximate length of the driven element of a Yagi antenna? Answer, about a half wavelength. So this is basically a dipole antenna, half wavelength dipole antenna. Question, how do the lengths of a 3-element Yagi reflector and director compare to that of the driven element? Answer, the reflector is longer, the director is shorter, and by about 5%. Question, which of the following would increase the bandwidth of a Yagi antenna? Answer, larger diameter elements. So these things are made of you know, aluminum tubing for strength, but if you made that diameter, and if you make the, and this is a sort of another point. We talked about vertical antennas before. They're also made of aluminum tubing, right? And the more diameter you have here, the wider the bandwidth you'll have that antenna will be. So question, which of the following would increase the bandwidth of a Yagi antenna? Answer, larger diameter elements. And by manipulating these distances, like the distance between the booms or between the elements and the number of elements. So this is a 3-element, but if you had, you know, you could have another direct, well, it's got to be straighter than that. had another director out here, which would be a little bit shorter, you'd get even more gain in this direction, right? So question, how does increasing boom length and adding directors affect the Yagi antenna? Answer, gain increases. Question, which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna? Answer, all of these choices are correct. Physical length of the boom, the number of elements on the boom, and the spacing of each element along the boom. And you know, you get these antenna modeling programs. If you're interested in antennas, I'd suggest you get one. There's one called, it's free. It's MM something or other. I should have wrote that down. But you can get it. It's free, and then you can play around with all these things. You can, you know, it'll ask you what the lengths here of these elements are and what spacing, and you can change them, and it'll generate the radiation pattern for you. And you can see how all these factors affect the performance of the antenna. It's very kind of cool.
I got a question for you. What if they were solid elements?
Probably you still have a similar kind of thing. The wider, the bigger the diameter, the wider. And why is that? Because RF energy is runs close to the surface of a conductor, so the solidness really wouldn't matter. And you get down to practical things, you wouldn't want to make them solid because the antenna would just be too heavy. Because you know, like these tubes are like, you know, 1/2 inch to 2 inches in diameter for strength purposes. Because if you know, a 20 meter Yagi, right, this distance is going to be like 66 feet. Or no, 33 feet. So that's pretty long. Especially since there's no support at the ends here. What?
That sounds good. That's a good reason.
Yeah. So there's a question. There's a question here about stacking Yagis. So you know, Yagis work great, but you can stack one on top of the other and turn them, and that increases the gain and directivity even more. This question: how does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength apart typically compare to the gain of a single 3-element Yagi? Answer: approximately 3 dB higher. So you go to all this work to putting up a second antenna and you get only a lousy 3 dB. And you know, chances are you're not going to do this on 20 meters, but you know, you might do that on 2 meters because these aren't that big on 2 meters. Question: what is an advantage? In fact, then they not only stack them vertically, but then horizontally. So you might have a whole nother stack like this horizontally, right? And by turning and twisting all 4 of them at the same time, you get an even more directivity and gain.
She's okay.
Question: what is an advantage of vertical stacking of horizontally polarized Yagi antennas? Answer: it narrows the main lobe in elevation.
Hey, Dan.
Yep.
Can you stack multiple ones that are for different bands? So you could have like a 70 centimeter and 2 meter like on top of each other for something.
You can do that, and they're usually not going to affect one another.
Interesting.
Yeah, and you know, the reason for that is that they're just not resonant. So the impedance at that frequency is going to be pretty high. So it's not going to have an effect. That's why. Well, I should have shown this in the dipole section. You can have an antenna called a fan dipole, right? What's that? So you got the center insulator. If you have 40 meter wires, 20 meter wires, and they connect to the same center conductor, and you have one coax, you get 2 bands out of 4 pieces of wire in one coax. Why is that? Because you said 20 meter signal up here, it's going to really go into these wires and maybe a little bit into these wires, but the impedance is so high that that's not going to have much of an effect. The same thing would happen here. If you had a 2 meter Yagi, well, you put the smaller one on top. A 440 meter Yagi over a 2 meter Yagi, you get the same thing. It wouldn't have the same, it just wouldn't cause much of a problem. And somebody, when they put up the antennas at the University of Michigan Amateur Radio Club, the guy who was the president at the time was a double E grad student. And he actually did the modeling. And he was able to show in the modeling program that stacking them like they intended to, again, they had little effect on one another.
Why do you put the bigger one on top?
You put the smaller one on top.
Or a smaller one. Why is that?
Just because you want the less weight, so
Oh, sure. Yeah.
Yeah, you get the idea. I mean, when you get to antennas, you kind of want to think electrical thing, right? But no, you got all these mechanical issues you got to deal with too. So it's a mechanical issue more than an electrical issue. All right. So if you have a 3-element Yagi, one problem that you run into is that the impede, you got a half wavelength driven element and you expect a feed point impedance of 72 ohms. But because of the interaction of the elements, that impedance really goes down. So what do? You have to have some kind of match at the feed point to bring that impedance up to 50 ohms. And these are two ways they do this, with what's called a gamma match and a hairpin match. The gamma match is so-called because it kind of looks like a gamma, right? You get, whoops. What am I drawing? What layer am I drawing on here? Oh, well. Kind of looks like a gamma, right? Here's the wire. It kind of looks like a gamma. They call this a gamma match. And then this is called the hairpin match because it kind of looks like a hairpin. There's two questions about this. Which of the following is an advantage of using a gamma match with a Yagi antenna? Answer, it does not require that the driven element be insulated from the boom. And I never really understood this myself. So I wouldn't be much help in answering this question. I mean, when you see this, I mean, it looks like this too. This is a half wavelength and it's not broken. It's just one long piece, one continuous piece. And I think it's just because the two sides make contact at this distance, that's what gives you the proper impedance. It's kind of confusing to me, to be honest. I've never had a beam antenna. This one makes a little bit more sense to me. It's called a hairpin match. What is a beta or hairpin match? Answer, a shorted transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. So, when you got a coaxial cable, right, and this is gonna, the current's gonna go into the element, but some of the current's gonna go this way, and that's what gives you the proper impedance at the feed point. They're just two questions, so just memorize these answers. Don't tell anybody I told you that, though. So next is a couple of questions on the quad antenna. This is also a directional antenna. This one is actually a 2-element quad antenna. And again, you have a driven element and a reflector. You don't have a director here. But this 2-element antenna gives you about the same gain as a 3-element Yagi. And like I say, each of these elements is about one wavelength long. It's about a 1 wavelength loop. So question, approximately how long is each side of the driven element of a quad antenna? Well, if you got 4 sides, each element's going to be about a 1/4 wavelength. What configuration of the loops of a 2-element quad antenna must be used for the antenna to operate as a beam antenna, assuming one of the elements is used as a reflector? That's a long question for what they're asking. But the answer, the reflector element must be approximately 5% longer than the driven element. So just like the Yagi, the reflector is a little bit longer. How does the forward gain of a 2-element quad antenna compare to the forward gain of a 3-element Yagi? Answer, about the same. So that's why this is a nice choice if you can figure out how to do it, because you only need 2 elements instead of 3 elements to get the same amount of gain. One problem, of course, is that you've got to support it. So it's again, it's a mechanical thing. You got to have these spacers to support the wire. And then the wire, if this is wire and it gets icy, these are sort of prone to mechanical problems, but they can be really good antennas. Any questions? Okay. So I don't have any pictures for the rest of these, but we'll just go through them. There's a bunch of questions here about sort of specialized antennas. I call them that in the study guide. First one is called the inverted V. And really it's a dipole antenna, but with only a single support at the center. And if you angle the elements down and you get it to be about 45 degrees, you get about a 50 ohm impedance at the feed point instead of 72. And instead of the figure 8 pattern, you get a more, this is acting more like a vertical here. You get a pretty much omnidirectional pattern. So question, what is the common name of a dipole with a single central support? Answer, inverted V. Another type of antenna that is kind of popular, and I was going to put one of these up myself before one of my trees fell down, is a loop antenna. So if you had a bunch of trees, you could put up a loop antenna. And you want to make this at least a wavelength long at the lowest frequency you're going to operate. So if this is going to be used on 80 meters, you want about 266 feet. Question, what is the combined vertical and horizontal polarization pattern of the multi-wavelength horizontal loop antenna? Answer, virtually omnidirectional with a lower peak vertical radiation angle than a dipole. So these actually can be very good antennas, even if they're low. They have very good, very low takeoff angles, which is good for DX, right? Low takeoff angles equals good DX. Next type of antenna is called the log periodic antenna. And this antenna kind of looks like a beam antenna, but it has a lot more elements. No, that's not really drawn to scale, but it has a lot of, and these elements shorten in a logarithmic fashion. That's why they call it a log periodic antenna. the nice thing about this antenna is that it can have a very broad bandwidth. So one guy here in Ann Arbor put up a log periodic antenna. It covered from 10 megahertz to 30 megahertz without tuning. I mean, it just, the way it was designed, it gives you that bandwidth without having to tune it. I mean, it's almost like magic, really. That's the, now you understand my understanding of some antennas. But question, which of the following describes a log periodic antenna? Answer, element length and spacing vary logarithmically along the boom. And they're not evenly spaced either. So I didn't space it properly here, but they're spaced differently too. Question, and in fact, most TV antennas were log periodic. Why? Because, you know, the TV band is kind of wide and you don't want to tune it. So they were designed to be log periodics. So they might look like Yagi antennas, but they're actually log periodics. Question, which of the following is an advantage of a log periodic antenna? Answer, wide bandwidth. So, you know, you get that wide bandwidth there. It covers all those bands. Instead of having tuned elements for particular bands, you just cover them all. What's the disadvantage? Well, so a Yagi might have a radiation pattern, something like this, but you're not going to get the same gain out of a log periodic. So the log periodic would have less gain and less of a forward to front to back ratio. But you get that wide bandwidth, and that's like a big deal sometimes. Any questions about that? All right. Here's another antenna called the near vertical incident skywave antenna. And this is really just a dipole antenna that's close to the ground. And what happens is you get ground reflection. So, you know, you get radiation this way, but then reflection. And so what happens is you get a very high angle of radiation and you get very close in propagation. So that's what you get with a near vertical incident skywave antenna. You might want to put, you know, like for example, there's a guy here in Ann Arbor who does a lot of emergency communication work. He wants to be able to talk to people around the state of Michigan on 80 meters. So he has a low 80-meter dipole to do this kind of thing. It allows him to communicate with people that normally even an 80-meter signal might skip over. Question, which of the following antenna types will be most effective as a near vertical incident skywave NVIS antenna for short skip communications on 40 meters during the day? Answer, a horizontal dipole placed between 1/10 and 1/4 wavelength. So this should be between 1/10 and 1/4 wavelength. And I noticed this myself. This doublet antenna I keep talking about, it's actually pretty low for as far as 80 meters go. It's between 1/10 and 1/4 wavelength. Although I have a funny situation in my house because my house is on a hill and there's a slope and it's hard to know exactly how far above ground it is, but it's pretty low for 80 meters. And often, I've not worked really any DX on 80 meters, but I have worked a lot of guys that are close. Even today, this evening, I worked a guy in Cleveland and in the Cleveland area. So that's pretty close. And normally this HF signal would skip right over that. Now we'll talk about receiving antennas. One of you had a question about receiving antennas. There's an antenna called the beverage antenna. And no, this isn't a vertical made out of beer cans, although there have been verticals made out of beer cans. A beverage antenna is a long antenna, at least a wavelength long, but it's very low to the ground. 4 to 8 feet maybe. And what's the use of this antenna? Well, again, it's good for receiving because it's directional off the end, and it's actually a very inefficient antenna. But that's a good thing in sometimes in receiving where you have a lot of noise because it won't receive as much noise. So this is a receiving antenna. We tried putting one up at field day, but we couldn't get it long enough, I think. I think that was the problem. Anyway, question, what is the primary use of a beverage antenna? Answer, directional receiving for low HF bands. But it's a wavelength long, so you gotta have the space for it, 160 meter antenna, beverage antenna, would be like 500 feet long. Again, we talked earlier about multi-band trap dipole antennas, right? Or vertical antennas. The way these things work is that you have a vertical antenna, but you have traps, what are called traps. And how does this work? Well, so you connect the coax here, and these traps are designed to basically be band stop filters, right? So this would be like the 10-meter trap. And if you send a 10-meter signal into it, only this portion of the antenna would radiate. It would just stop right at that, the signal would stop right at that trap. This might be the 20-meter trap. So for a 20-meter signal, you're going to use this much of the antenna. This might be the 40-meter trap. So on 40 meters, you're going to use this much of the antenna. And the whole antenna might be 80 meters. So that's a multi-band trap vertical. Question, what is they say one of the disadvantages is poor harmonic rejection. That's the question here. Which of the following is a disadvantage of multi-band antennas? Answer, they have poor harmonic rejection. Well, why is that? Well, if you had a 20-meter signal, or a 40-meter signal, let's say, the second harmonic is going to be on 20 meters, and this antenna is resonant on both. So it's going to radiate both the primary signal and the 20-meter harmonic. Whereas if it was only resonant on 40 meters, this harmonic would be, we just wouldn't have that much radiation on 20 meters. Question, what is the primary purpose of antenna traps? Answer, to permit multi-band operation. Let me stop my sharing here for just a second. Wait, I'll do this.
Is that the dog snoring?
I don't know. That's what I was going to do, is mute that. All right. So if you want to ask a question, just unmute yourself. Any questions about multi-band trap verticals? We already answered the next question. What is the feed point impedance of an end-fed half-wave antenna? Answer, very high. Another type of antenna that is sort of become popular lately, but again, I'm not real high on them, are these small loop antennas. So they require a big capacitor, tuning capacitor here, because they're electrically small, so the voltages can get quite high even at low input power. The nice thing about these, and sometimes they're used as receiving antennas, which they're good for, but like I say, they're not that efficient. They are small though. That's the whole thing. Sometimes they're like a third of a wavelength. And, you know, a third of a wavelength in 20 meters is what? It's like 7 meters. And then, you know, the diameter for a 7 meter loop is not that great. It's like 7 meters divided by 3.14. It's like 2 meters, 2.5 meters maybe, right? So they're not that big, but they can be. They're just fussy. They're very fussy to tune, for one thing. But they are directional too. So question, in which direction or directions does an electrically small loop, less than 1/3 wavelength in circumference, have nulls in its radiation pattern? Answer, broadside to the loop. So you'll be receiving things like going into the screen and in the back of the screen, but to the sides, that's where the nulls are. Again, if you use them as receiving antennas, they're not so bad. When I was a kid, you know, I would listen to actually AM broadcast stations. I would try and hear them as, you know, far away as I can. And I actually built a loop antenna, and I, you know, had multiple turns of wire, and there was a tuning capacitor here, and it worked pretty well for receiving AM stations, and it was only like it was about 3 feet on a side, I think. So it wasn't that big compared to, you know, an AM wavelength. An AM is, you know, hundreds of meters, and you know, this worked pretty well. So this is more of a receiving antenna than a transmitting antenna, although some people are trying to get them to transmit as well. Question, how does a screwdriver mobile antenna adjust its feed point impedance? Answer, by varying the base loading inductance. So these things, if you look at them, the big coil here, and then like a whip section. And they actually have, I think they have a slug that goes up and down and it's motor driven, that goes up and down in here, which varies the impedance of this loading coil. And that's how they tune this system. And it's called a screwdriver because the slug here that's driven up and down is on a sort of a screwdriver drive mechanism. So it's called a screwdriver. And lastly, a halo antenna. We call it a halo antenna because it's circular. And it's about a half wavelength, I think. And there's a space there. So it's kind of a bent dipole. And if that's sort of the top view, if you look at the side view, it's, you know, very flat. Question, in which direction is the maximum radiation from a portable VHF, UHF halo antenna? Answer, omnidirectional in the plane of the halo. So omnidirectional around the antenna. I actually built one of these when I was a kid because we had a 2 meter, the club I belonged to had a 2 meter AM net, you know, and there were these things from Heathkit you could buy called the Benton Harbor lunch boxes, because they look just like a lunch box. And I bought one of those, and I built one of these 2 meter antennas, and I was actually able to talk to the guys on this 2 meter AM net. I'm still, that was actually the first antenna that I built myself. So I'll always remember that very fondly. The 2 meter halo antenna. And with that, we're done for the evening, unless you guys got questions. None?
I guess the only question is one more chapter for next class then?
Yep, let me look and see what it is. Radio wave propagation.
Okay.
Very good. Good night, everybody.
Yes, good night. It was good.
Thanks, Dan.
Thanks, Dan. Good night.
Good night, everybody. Enjoy yourselves.
Good night. Thank you.
73.